18.1 Applications of differentiation in kinematics. Okay, so now, for those of you who are doing physics, you know the displacement of an particle is defined as a change in position of particle. So basically, what we know as distance. Okay, now we use the word displacement, but the difference between distance and displacement is such that for distance is always a positive, but for displacement it can be negative. What do I mean? So for example, if let's say there is a particle that is traveling along a plane like this, so this is the initial displacement. Let's say the particle is initially here. Okay, this starting point. The displacement, which we use the letter s, is equals to 0. If the particle, okay, we define to the right as positive and to the left as negative. Let's say the particle, okay, in this red dot, the particle ends up here, and this distance right here is 5 units. Then we say that the displacement here is equals to 5. Okay, let's say cm or something. Okay, but let's say if the particle now travels, okay, to the left of the initial point here, let's say it ends up here, and this distance, the displacement now can be s is equals to, let's say maybe this is -1, is equals to -1 cm in itself. So the displacement is relative to the initial point in which, so we have to define where the initial point is, and how far away it is, whether is it to the right or to the left, will determine the displacement, right, of a particle itself. Okay, so for example, let's say I am given a displacement, right, of s equals to 4t minus t squared for 0 t between 0 and 5. So let's say I'm using s is equals to 4t minus t squared. So when t equals to 0, the displacement is equals to 0, and that is given by this point over here. What happens at t equals to 1? Okay, so if we substitute, all right, let me use a different color. S equals to 4t minus t squared. So when t equals to 1, the displacement s is 4 times 1 minus 1 square. So it's equals to 3. So notice that the initial point is here. The object or the particle is now 3 units away, or 3 meters away from the starting point. And it is positive 3. Why? Because it lies to the right. We define the right as positive. What happens now, okay, if we have a case whereby the t equals to 5, as I wrote down here? What about t equals to 5? So what I have is s equals to 4 times 5 minus 5 squared. Notice the displacement is -5. Before I draw it out for you, can you place, okay, where the particle is at t equals to 5? If you're able to tell me that the particle is here, so that means, right, at in real time at t equals to 5, the displacement itself is -5. So that's where the object is, okay, at different points in time. So for example, okay, okay, at t equals to 0, the object is here. At t equals to 1, the object is here. Then eventually the object will move, and it finds that at t equals to 5, the object is actually down here in itself. So don't get confused by these points. These points only show you the particle at a given time. So at t equals to 0, the particle is here. T equals to 1, the particle is here. And after t equals to 1 has passed, the particle is no longer here. At t equals to 5, the particle is here. So all these is the same particle, not 3 different particles. Okay? Okay, so basically is this. So now if the displacement s is positive, it has moved along the positive x-axis. If s equals to 0, is at the starting point O. If s is less than 0, it's a point at the negative x-axis. Like what I said, it has moved in the other direction itself. Okay, velocity is defined as the rate of change of displacement. Here's the very first thing that you need to know. So given displacement, okay, if I differentiate displacement with respect to time, what I actually get here is the velocity. So from displacement, you differentiate, you get velocity. And this is given by v equals to differentiating s with respect to t. So for example, okay, what they give you here is the displacement is 6t minus t squared. That's the equation governing the displacement. So to get velocity, what I do is I differentiate. So what I do is my velocity is you differentiate s with respect to t. What I get is 6 minus 2t, which is what I've written out down here. So let me just erase this. This is the same thing. So now I'm going to find 6 minus 2t. I'm going to try to get, okay, the displacement, okay, sorry, the velocity at different points. For example, in the one at green, okay, my displacement is 5. Just to recap how I get this 5, I put t equals to 1 into my displacement equation. Now I want the velocity. Okay, so velocity is 6 minus 2t. So it's 6 minus 2 times t, so my velocity is 4. So that means at this point in time, when the particle is here, the displacement is 5, the velocity is 4. Notice that velocity and speed, okay, is the velocity is a vector, means that there is a direction. So it's moving towards the positive direction, it's moving to the right at 4 meter per second. Okay, so it's moving towards the right. Now, if you notice, there are some points like t equals to 3. What happens? So the displacement is 9. Okay, how I get 9 again is t equals to 3. I put into here 6 times 3 minus 3 squared equals to 9. That's why my displacement is 9. So that means if you want to imagine, what's happening is there is a particle like this. Okay, I just drew the particle, this particle here. So at t equals to 0, the particle is here. So the particle will move. At the first second is down here. Second is here. Third second it comes here. Okay, third second it comes here. We draw the U-turn here. It's not actually U-turning. It's actually moving along the same plane. So t equals to 0 is here. T equals to 1, it is here. T equals to 2, it comes to here. T equals to 3, it goes here. Then t equals to 4, it goes backwards, it comes here. T equals to 5 is here. T equals to 6 is here. T equals to 7 is here. So I know this looks like a 3D or a 2D plane, okay, but it's just moving along the same line. But we cannot draw along the same line, that's why I have to draw this U-turn thingy down here. Okay, so now back to the question at hand. What happens at t equals to 3? So my velocity at t equals to 3 is 6 minus 2 times t. My velocity is equal to 0. So 0, if there's no velocity, means that the object or the particle has come to a complete stop. So at this point here, when velocity is 0, the object has stopped. In kinematics, right, when the object stops, what is it doing? When it is stopping, it's stopping to turn around. So it means, right, when the velocity is 0, okay, the object is actually trying to turn around. So it is after t equals to 3, the object turns around. So for example, okay, at t equals to 4, okay, so now at here, t equals to 4, my velocity itself at t equals to 4 is 6 minus 2 times 4. My velocity is negative 2. So it's still moving, okay, at 2 meter per second, okay, but what happens is it's moving in the other direction. So after it stops, okay, the object will actually turn and it starts moving in the other direction. So just to give you a final example, like example at t equals to 6 itself, the velocity is 6 minus 2 times 6. The velocity itself is negative 6 meter per second. It's moving towards the left itself. So basically, when the velocity is positive, it's moving in the to the right, okay, or in the positive s direction. When v equals 0, it is stop. So the special thing you need to know that when it stop, what is it doing? It is turning around. Okay, to go the other way. Okay, then when v is less than 0, it's moving the other way. Okay, now just one example 1, okay, for 18.1 first. So in example 1, what we have here is this. Find the value of t when the particle first comes to instantaneous rest. So basically, instantaneous rise implies that v is equals to 0. So first we start with s is equals to t times t squared minus 12t plus 36. Okay, what I'm doing here is I'm just simplifying to make my life a bit easier. Okay, so this is the displacement. So now velocity. How do I get velocity from displacement? I will differentiate. So I differentiate displacement with respect to time. Get 3t squared minus 24t plus 36. Now, in order for me to find when the particle first comes to instantaneous rest, so I need to find velocity equals to 0. Since I already know that velocity is given by this, so what I'll do is I take 3t squared minus 24t plus 36 is equals to 0. Make life easier, divide everything by 3. Then what I can do here is I get t minus 2, t minus 6 equals to 0, t equals to 2, or t equals to 6. Both of these answers means that the velocity of the particle is 0. But remember that the question says where it first comes to instantaneous rest. So where is the first instance? So the first time is at t equals to 2 seconds. Okay, so we don't choose 6 because when it's the first time. So is at t equals to 2 seconds. Now we want to find the value of t. Okay, so the particle returns to O. Okay, returns to O means that the particle was moving. Returns to O means it's at the start. At the start, what do we know? At the start, we know that my displacement S is equals to 0. Hence, S equals to t minus 6 squared. So for part 2, at O, the displacement is 0. t minus 6 squared is 0. So t equals to 0, or t minus 6 squared is 0. T equals to 6. So at 0 seconds, okay, is at the starting point. At 6 seconds is at the starting point again. Means that it has traveled, then go backwards until it reached the starting point. Okay, the starting point here, and this point here is when t equals to 6 seconds. The starting part is t equals to 0 seconds, so the particle is moving in this way. Okay, so that means, right, the value of t, so in this case the value of t is equals to 6. Now the distance traveled, right, from t equals to 0 and t equals to t itself. So be careful here. So the distance traveled from t equals to 0 and then it returns to the origin again. To solve this question, what we will need to do is to draw a diagram itself. Okay, now, so remember, okay, when did it first turn? Okay, it first turn in part 1 we learned that first turn when the velocity is 0, it turns at t equals to 2 seconds. So basically, if I were to draw, okay, if I just use a simple diagram first, okay, so this is the origin at t equals to 1. Let me just use some really cheapskate animation. It is moving forward. T equals to 1 second, t equals to 2 seconds. It will stop. Okay, then once it stopped, what is it doing? It is going backwards. Then just now we learned that at 6 seconds it passes the origin again. So that means okay, see again at 0 seconds the particle moving, okay, until 2 seconds it stop. Then stop, what does it do? Change direction. You start moving backwards until at 6 seconds it's back at the origin. Then you continue to move again. Can, so that's what the particle is doing. Okay, so now, okay, when sorry, okay, oops. So what is happening here is this. Okay, so the particle is actually moving, okay, forward. Then at t equals 6 seconds it goes backwards again. So now the distance, right, from 0 to t, so what I can do is here I will draw the particle. This occurs at t equals to 0. So it will move until it comes to a complete stop. At a complete stop, this is t equals to 2 itself. okay, t equals to 2, my displacement here, this is displacement. So my displacement when t is equals to 2 is equal, we will have to find that later. Then don't forget that the next part of the journey, the particle will continue to travel backwards, okay, until 6 seconds. So at this point, okay, at 6 seconds, the particle is down here itself. Can? So now what I'm going to do here is this. I'm going to focus on this portion here. Okay, when t equals to 0 to t equals to 2. Alright. So now, okay, so the distance, okay, from t equals to 0 to t equals to 2. So the displacement is equals to t is 2, 2 times 2 minus 6 square. 16 times 2, this is 32 meters. So this first portion that are highlighted in yellow is 32 meters. Then after I know that it stops completely, the velocity is 0 at t equals to 2, then it starts to go backwards, okay, then it travels backwards until it comes back to origin. So how much has it traveled? From here to here, it travels 32 meters. From here, from here to here is 32 meters. Then from this point, it U-turn backward until you go back to the starting point. This will be another 32 meters. Hence, the total distance it travels. So the distance, so it's not displacement, it's distance. So distance traveled here is 32 plus 32 is equals to 64 meters. Okay, so that is it, right, for example 1. Now please try 1 itself, all right, and then I can help you all with the thing. So just pause the video now. When you're ready, unpause and give you the answer. Okay, for the first part here is this. The speed of p after 1 second, since we are given the displacement itself, differentiating will give you the velocity. Okay, so now the velocity after 1 second, you sub in into the velocity, t equals to 1, the speed is 6 meter per second. Now, when the particle is at rest means that velocity is 0. So I take my velocity function equals to 0, t equals to 2 seconds. Hence, the particle comes to rest at t equals to 2 seconds. So again, it will be helpful if I show you a diagram. So basically, let's say there's a plane here like this. Then here, this is the starting point. So the particle will move until it, after 1 second is 6 meters per second. After 2 seconds, it comes to a rest. Okay, 2 seconds, it comes to a rest. Rest means it U-turn, then you go back here again. So the distance, okay, from p, okay, when it first come to a rest, okay, is at t equals to 2. So when t equals to 2, I sub in into my displacement equation. So what I get is 12 meters. So therefore, okay, if you can just imagine here to here, after 2 seconds, it has traveled, okay, here to here is 12 meters. Can? That's why for part 2, here t equals to 2 when the distance is 12 meters. Now, this question here is t equals to 3. So at t equals to 3, it will stop at t equals to 2, it U-turn. So I need to find out t equals to 3, where is the particle. So now, bit by bit first, let me just draw this for you. So this is 0. So at the start, the particle is here. At t equals to 2, it has traveled 12 meters. So here, like this, okay? So the particle will be here. So at this point here is t equals to 2. My displacement s equals to 12. So here is 12 meters. Now, as I have said, okay, at this point when it's at instantaneous rest, what is it doing? It's U-turning and going back. So I need to know, right, how far it has gone back by t equals to 3 seconds. So what I'll do here is at t equals to 3 seconds, my displacement s is 12 times 3 minus 3 times 3 square. So what I'll get here is 9 meters. Okay, be very careful. Okay, here is the one that you all tend to make errors. If I say that this distance is 9 meters, is this correct? Okay, this distance here is not 9 meters. Where is this 9 meters? Okay, just to be very clear, this 9 meters actually is over here. Okay, so the particle at t equals to 3 seconds, the particle is somewhere here. So where is this 9 meters? 9 meters is the displacement or the distance the particle is away from the origin. So actually this 9 meters is right here. Okay, this is 9 meters. So therefore, the second part of the journey, after it U-turn, it will come here like this. Okay, so first part, okay, and second part. So the first part, okay, see my the laser pointer, the distance here was 12 meters. So for the first part, okay, what has happened is that it has traveled 12 meters. Then, okay, the next part is this blue color part. How far is this blue color part? Here to here is 9. Here to here is 12. Okay, minus away 9. So this portion here is 3 meters. So the distance here that's traveled right here is 3 meters. Hence, the black color portion is traveled 12 meters. Then after that, it U-turn, it goes backwards. This portion here is 3 meters. Hence, the total distance traveled is equals to 9 meters plus 3 meters. Total distance traveled itself is 12 meters. All right.